Alright guys, today we are going to start on the next half of this chapter, and today we're going to begin with concentration, which basically tells us how much solute is in the solvent, like how much to be dissolved. This is how we actually quantify or measure the exact amount of something that is in solution. So in other words, instead of saying, oh, it's really strong, or oh, it's really quite dilute, we can say with some accuracy and precision exactly how much stuff we got dissolved. All right, so let's just dig right into this. So concentration is the amount of solute compared to the amount of solvent. And we have different ways of measuring this concentration based on like the situation, you know what I mean? Most of the time in our lives, we use this thing. We use things that are qualitative. And qualitative just describes, just sort of like gives us a general idea. And that's fine for everyday life. You know, it's like, did you make the Kool-Aid too strong? Is it too concentrated? Or is the Kool-Aid too dilute? Or is it perfect? You know, it's like, it's all these things that just sort of describe it. They're like, you know, it's really sort of opinion-based, really. But the other thing, the one that science wants, is this one. It's quantitative. Quantitative. Now, quantitative tells us, or gives us a measurable amount. I want you to see this, right? It's really close to starting out with the word quantity, right? And that's why it's called quantitative, right? And also up here, qualitative, it almost starts out with quality, right? So qualitative describes or tells us the quality, where quantitative gives us a quantity, an actual measurable amount. So for science, for chemistry, the two major ones are molarity and parts per million. But there is one more that is like used quite often, and that is percent. Like I was saying, percent composition. That's the third one that we need to know. So let's just dig right into them, right? So the first one, molarity, this is sort of like the chemist's concentration, right? Because this tells us how many moles we have, right? This describes moles, and moles, like, again, relates to how many particles we have, which is what chemists want. We want to know how many molecules are in there so we can get the right, like, balanced ratio of molecules. If you remember way back when we talked about chemical equations, you got to get the right ratio of reactants so that the reaction can happen. So we use molarity quite often. Now here's a couple things. Molarity, which is capital M, is equal to moles divided by liters. Liters. So here's a couple things. First way that this can be made difficult is if it's given in grams. If they give you grams, you got to convert it to moles. Got it? And now the second way is if they give you milliliters. If they give you milliliters, you must convert it to liters, because that's sort of like the definition of molarity, is it is moles of particles per liter of solvent. Got it? Great. Now this is for like normal concentrations. You know, this is for like stuff that actually like dissolves in water. However, like we talked about with lead, there are some things that that don't dissolve in water. You know, but they still do. But in very, 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 very small amounts. And that's where this guy, parts per million, come in. Now, parts per million is all about mass. ppm, parts per million. Now, this is equal to the mass of your solute divided by the mass of the solvent. And then you multiply that ratio by 1,000,000. Right? So basically what this tells us is that the ratio of solute to solvent is like teeny, tiny. Very, very small. So instead of using like a crazy small decimal, we multiply it by 1,000,000 and we get a slightly more reasonable number. Again, this is used for like solutes that are in very, very, very small concentrations. Now, if you have something that is not in a small concentration, but you don't necessarily care how many molecules there are, we use for that percent mass. Now this is what's most commonly used by like non-chemist people, right? So if you look at like a bag of saline in a hospital, it has, you know, the sodium chloride measured by percent mass. if you're a pharmacist and you're mixing up a concoction of like antibiotic, it's measured by percent mass because they just, the work has already been done. They just need to know how to mix it properly, right? So percent mass is mass of solute divided by the mass of the entire solution. Lock in on that one, guys. It's the entire solution. This will be clear later on when we start doing some of these problems. And then, of course, it's a ratio, so you just like multiply it by 100. Now, how the heck are you supposed to remember all three of these equations? I don't know, because there's no need. They're all on the back of your reference table. Now, the other one that is not on the back of your reference table is percent volume. But I want you, before I go there, I want you to take a good hard look at this equation right here. Right? And now look at this one. I'll give you a minute. You see anything similar? Yeah. So percent by mass is exactly the same as percent by volume. Percent volume is exactly the same as percent by mass. Just one uses mass, one uses volume. Got it? Okay. Again, the one thing you got to be careful for with the percentage thing is that it is the volume of the entire solution, right? So the volume is both the volume of the solute and the solvent combined. Got it? That is actually really important to remember. So let's just do this. Excuse me. You want to do a couple of these? I think I do. Wait. Right. Okay. Now I'm ready because this is not like I'm not going to do this math in my head. Okay. Find the molarity. I think I know what equation we're going to use. Of 100 ml solution that contains 0.25 moles of solute. Okay, as always, we're going to take a word problem and we're going to write out the variables first, right? So if it says find the molarity, there it is. There's my M for molarity, and it's got a question mark. Of 100 milliliters, I've got 100 milliliters of the solution and 0.25 moles. Okay, so what equation could we possibly use that uses like molarity, milliliters, and moles, milliliters? That's not good, right? Because if you recall, molarity says that we must be using liters, not milliliters. All right, because if you use milliliters, the answer is going to be like weird. So we're going to use the metric system and move the decimal place 3 times. 1, 2, 3. So it'll be 0.1 liters. That's why we like the metric system. Okay, so going back. We've got molarity, we've got liters, we've got moles. I think it might be the molarity concentration, right? So if you remember, it's really a good idea after you write out the variables to jot down the equation you're going to use. That way you're not doing the back and forth. Just trust me. This is what how we like eliminate all the problems I've been watching people and mistakes people make for the past. I don't even know how long I've been doing this. Way too long. I'm too old. Anyway, so let's just plug in let's just do like the plug and chug thing now. So now we got molarity. That's our missing variable. It's going to be 0.25 divided by 0.1. Molarity equals, nice, easy peasy lemon squeezy. I'm telling you, man, the way that we do this, the way that you get these right every time, is by first writing out the variables with the question mark. Second, write down the equation you're going to use. Third, do your substitution thing. And the reason why I insist on number 1 and number 2 is because that way you know that you'll be using the exact right equation. What people tend to do is they just get this idea that they're doing concentration, so they lock onto one equation and just shove numbers in there and try to make it work. This isn't math class. This is science class where you have to choose which equation you're going to use. You guys get what I'm saying? Lovely. Let's move on to the next one. And let's use, what color should we use today? I like purple. No, let's not do purple. Let's do orange. Okay. What's this one say? What is the molarity? All right. Okay. M. What is the molarity of 250 milliliter solution? I'm switching that straight to liters because I can. That contains 4.0 grams of dissolved sodium hydroxide. All right, so I'm seeing molarity. We're given volume. Now, we don't have moles, though. That's kind of a problem. But remember, what did I tell you about the molarity equation? Right here, let's go back up to like visit one more time really quick. There it is. Often, what they're going to do is they're going to give you grams of your substance instead of your moles. And so you're going to have to convert grams to moles to pop it into the equation. Does that make sense? It's just a little like, well, it's a way to make it more tricky, but it's also closer to reality. I mean, that's, you don't scoop 5 moles of a like a salt out of the bottle. It's, you know, you measure it on a scale. So the grams is a little closer to what reality is. So before we can use this equation, right? So the equation I would want to use, I'm going to want to use molarity equals moles per liter. But before I can do that, I'm going to have to take a little time out, and I'm going to have to use the lines of pain here. So if we have 4.0 grams, I'm going to put that in the upper left, and I'm going to have to calculate sodium hydroxide. If you remember how to do this, it'll be pretty good. So remember, there's 1 sodium. Each sodium atom weighs 23.0, right? And we do this for each element. And then we multiply them, which in this case is pretty easy because they're all being multiplied by 1. And then we add them up. Boom! Gram formula match. You remember that? So this is going to be 40 grams per mole. Now, I'm starting with 4 grams, so I've got grams in the upper left. So in the bottom right, I'm going to put grams, specifically 40 grams, and up top I will put 1 mole. Lovely. So let me just get this out of the way here. Okay, and this is going to give us 0.1 moles, which I will then plug into my equation over here. So molarity is going to equal 0.1 mole divided by, and remember I took my 250 milliliters and I went 1, 2, 3 to 0.250 liters, 0.4. Awesome. Easy peasy lemon squeezy. All right, let's do this next one. See, this is different. How many moles? They're asking us how many moles. That's weird. That's different. So in this case, the moles is going to be the question mark. So how many moles of solute are dissolved in 30 milliliters? Oh, okay, so I'm going to convert this to liters right now. So go 1, 2, 3. I'll have to add a 0 there. So it'll be 0.030 liters of a 2.0 molar solution. Well, I think I know which equation I'm going to use. Got the molarity. Moles is my unknown, and 0.03. Let me double check that. See how easy that was? In this case, what was weird about this one was instead of finding molarity, this time our X was the moles, right? But the same process happens each time. You write out the variables first, and then we choose our equation based on not just what we think it might be, but based on the information that we were given. Beauty. Next, how many grams of silver nitrate, oh man, this is going to be a thing, are needed to prepare, okay, so let me come over here. Let's do this one. Grams, AgNO3, that's my question mark. How many grams of silver nitrate are needed to prepare 200 milliliters? 1, 2, 3. Oops. My volume is 0.200 liters of a 0.1 molar solution. Awesome. Okay, I think I know where we're going because we have molarity here, but the problem is we want grams of silver nitrate. Well, in this case, I can't figure out grams directly, so it'll probably be a 2-step problem because remember, grams and moles are easily interchanged. So the first thing I'm going to do is find moles with this molarity equation. Delightful. So I've got 0.02 moles of AgNO3. Now in this case, we're not done yet because this answer gives us moles, but what we need is grams. So easy peasy, man. We're just gonna like break out our lines of pain knowledge once again. We're gonna write down what we start with in the upper left. So we're starting out with 0.02 moles of Ag. Oops. 0.2 moles of AgNO3, sodium nitrate. And I'm going to need to find the gram formula mass here, aren't I? So let's crank that out down here. Okay. 269.9 grams per mole. So if I've got moles in the upper left, I'm going to put 1 mole in the bottom, and I'm going to put 269.9 grams. And that kind of math is way past my brain. So I'm going to... And there's my final answer. So in this case, the one that was weird, like what was weird about this is we had to get all the way to grams. So we had to first find moles, and then we had to convert moles to grams. And that's just how we got to grams. Easy peasy lemon squeezy. All right, ooh, a percent mass now. All right. So percent mass is pretty easy. It's part over whole times 100. So what is the percent mass? So let's do percent equals my question mark of a solution containing 2.3 grams ethanol, dissolved in 10.0 grams water. All right, so the percent by mass. The percent by mass, or percent, it's really percent composition, is parts over whole times 100. Now remember, it's like the entire solution, right? So in this case, if we're finding the percent composition of ethanol, our percentage will equal, well, the part that's from our ethanol is 2.3 grams. And then we got to find the mass of the whole thing, not just 10. Because 10 is just like the water. We need the mass of the whole thing, right? So the mass of the whole thing is actually going to be 12.3 times 100. You guys see this? Like, this is something I need you guys to lock into here, that it is the whole entire thing. That's how the percent composition, or the percent by mass, or the percent by volume works. It's part over whole times 100. The whole thing, not just like one part or the other part. So let's do some math here with a, not my brain. There you go, 18.7%, at least according to the calculator. Easy peasy, man. That was great. You guys get how that works? Man, don't drop the ball on this part there. Okay? Next one. All right, next, what is the percent by volume? All right, so it's still going to be my percent. The solution containing 18.2 milliliters of glycerin dissolved in 85.0 mils of water. This is one other little thing I want to show you guys. It's like a shortcut. So a lot of times we just switch everything to liters because that's our standard measurement of volume. However, with our percent composition, if we have milliliters in the numerator and milliliters in the denominator, they cancel out. So you can actually use milliliters with this one. As long as everything is in milliliters, we will be just fine. So what is our percentage here? The part that we're looking for is the glycerin, obviously, because that's like the little guy. So that'll be 18.2. And then we got to put the volume of the entire thing. So it's not going to be just 85, right? Because that's only the water. We want the percent volume of the whole entire thing. So that'll be 18.2 plus 85. Right? We're going to add them together. So because this tells us the volume of the entire solution. So then, now that we're set up, now that it's part divided by the actual whole thing, go to math. And then we write down the answer, and we're a boss. That's how that do. Oh, one more. All right. About, hydrogen sulfide. Not good stuff. Not good. So about 0.0035 grams of hydrogen sulfide are dissolved in 10 grams of water. Express this in parts per million. I think I know what equation we're going to use, but let's just do it anyway. Let's find parts per million. I've got 0.0035 grams of hydrogen are dissolved in 10 grams of water. All right, that's all I need. So the equation is parts per million equals part over. So here's the thing. With parts per million, you could do part over whole times 100, or you could just do the part, like the thing that you're looking for, like solutes over solvent times a million, right? Because if you look at it, like this, the solute here is 0.0035. It is so small compared to 10 that the mass that it adds is like negligible. Like it's almost not even there. So that's why we can get away in parts per million with just doing like the grams of solute divided by the grams of solvent. Because the grams of solute are so stinking small, they have almost no effect whatsoever on our final outcome. So when we plug this in, parts per million, it's going to be equal to 0.0035 divided by 10.0 times 1 million, or 1 times 10 to the 6. And let's math to find out what that answer is. I got, well, at least the calculator's telling me, 350 parts per million. It sounds about right. That's awesome. All right, we're done. Lovely. Hey, that was pretty easy. Once again, all of these equations are on the back of your reference table, so you won't have to memorize them. You will have to be able to choose which equation is going to be the right equation for your particular situation. So that's the thing. Find the equation for the situation. And there's two ways we're going to go about this. We've got finding concentration. We've got molarity. Finding concentration is just your percentages. The molarity, that's where we dig into molarity with, like, sometimes there's grams, sometimes there's moles, sometimes your answer has to be in moles, sometimes your answer has to be in grams. It's milliliters instead of liters. It's just messy. But I ain't scared for you, and I hope you have a super awesome day.